In this video, we're going to talk about really the heart of this unit about transformations of functions. So specifically, this video, we're going to talk about translations, in other words, shifts of a graph, either up and down, left or right, and vertical stretches and reflections. I would argue that everything that we're actually going to talk about, most of the things we're talking about in this video, you've already kind of explored already last year in grade 10 with respect to quadratics. The thing that we're going to take is all the things that you sort of learned with quadratics. You talk about the A value, we have vertical stretches and compressions and reflections. And then the H and K, you might have been using those variables for quadratic to indicate that the parabola has shifted to the left or right or up and down. We're just going to sort of extend that and really see that that applies to all the functions that we've talked about in the first unit or the first section when we talked about parent functions. So the cubic, the radical, the square root function, the reciprocal, and the absolute function. I think I said that reciprocal. But it's going to apply to all those, so we're going to go through some examples. The success criteria after this video, hopefully you'll be able to understand and recognize the following transformations of a function f of x. So we're going to see that there's going to be vertical and horizontal shifts, what we call translations. So there's no change in the shape of the graph, but it's just being moved. We're also going to look at vertical stretches and compressions. So this is when the shape actually changes. So it's almost like when we take the graph and we either pull it up and down to stretch it out or push it in from the top and bottom to sort of compress it. And the last thing we're going to look at is vertical reflections, or we can also say reflection in the x-axis. So this is when it's reflected up and down. So for example, when we had the parabola, when it was reflected in the x-axis, it opened downwards instead of upwards. So a new thing is that we're going to actually write a transform function in either function notation. So we're going to lean heavily on what we did in Unit 1 when we looked at function notation. So that's going to come heavy into this unit, and so we have to get a firm understanding of that. And then the next part is as an expression, which really isn't new, but really we should look at how to sort of go back from an expression to function notation and vice versa. So I'm going to start off with an example of, so here we're going to define a function f of x to be the absolute value of x. So we're really looking at a parent function, the absolute function. And we're going to have another function, v of x, which is really based off of f of x. In other words, it's going to be a transformation of f of x. And how we're transforming it? Well, we're taking f of x, in other words, the absolute value of x in this case, and whatever we get as an answer to that, we're going to add 3. And hopefully from this, we could see how this affects the graph and why. So we're going to go through a table of values. Oh, let me do the expression first. So we're going to write this as expression. So there's a typo here. There should be, our function is v of x. So how do we write this as an expression? Well, basically we want to take f of x, because here f of x could be any function. In this case, specifically the absolute. And we want to replace f of x with the actual function itself. So really it's as simple as f of x. In this case is the absolute value of x. And we just replace it with that and then plus 3. So that's v of x as an expression. What we want to look at as an expression here is because it actually helps us evaluate the certain points that we get so that we could graph this. So when we look at the absolute function, one of the things that we have to be really comfortable in recognizing the parent functions and some of the key points of the parent functions and how that parent function looks like. So the absolute function is shape of a V, and it has that really central point where it's the pointy end of the V, or the vertex if we want to call it that, and that happens when x is 0. So that's where we're going to start in terms of setting x. And then from there, with the absolute function, we're going to go up by 1. So 0, 1, 2, 3. And on the other side of 0, we're going to go down by 1. So -1, -2, -3. Now I'm going to just give some points for f of x, because here I'm just going to do this so that you could kind of see why we have the net effect of when we add 3. What we're going to see is that this graph actually moves up by 3. So if we calculate actually the f of x, in other words, the absolute value of x, so this is the absolute value of 0, so that's going to be 0. The absolute value of 1 is going to be 1, and so on. So we get 1, 2, 3. And here we're going to get the absolute value of negative 1. Oh, not the 1 too big there, which is going to be 1. Absolute value negative 2, which is 2. And the absolute value negative 3, which is going to be 3. So we know that this is what the parent function looks like. And while it's not asked, but I will graph it just so that we get a comparison. So let me put the scale on here. And so we get 1, 0, 0, 1, 1, 2, 2, 3, 3. And here we know that this is going to be a v, so these are connected by a straight line. And so that's f of x. That's my parent function. So what is v of x? Now I could just go off and use this equation and do all that work again. But really what we're saying is we're going to take the answer from the absolute value of x, so in other words, the answer from my parent function, and simply add 3 to it. So this was the advantage of why I actually chose to do the table of values for f of x as well, because I'm just going to take each of these and really add 3. Because that's what that kind of means. We take our answer of our function. So this is what we say is outside the function. So I'm going to use that a lot in this video, and also really the rest of the unit, because we're about talking about doing things to x doing things to x inside the function, or in this case, we're doing something to a function outside of it. In this case, we're adding 3 after we calculate the absolute value of x in this case. So here it's going to be negative 3 is going to be 6, 5, 4, and 3, because 0 plus 3 is 3, and then 1 plus 3 is 4, and then we get 5 and 6. So if we're to sort of graph this point now, negative 3 and 6, that would look like it's up here. And then negative 2 and 5, negative 1 and 4, 0 and 3, 1 and 4, 2 and 5, and finally 3 and 6. There we have our graph of v of x. And hopefully you can see that really this is really the blue graph, and it's being moved up by 3 units. And why we see that this is actually a shift, we call this a shift up by 3 units, is because simply we're taking every single answer from our function and we're just adding 3 to it. So there has a net effect of raising our values. If we're to subtract, let's say 5, again, we're going to take every single answer and we're going to reduce it by 5. So our y values are going to be 5 less. And so this is why this has a net effect of the graph looks like it's being shifted down. So this is what happens when we add or subtract something outside our function. So let's look at an example. And here we have the f of x is the square root of x. So that's going to be my parent function. And we have s of x is really a transformation of f of x. In this case, how is it transformed? Well, here we're taking 2 and we're multiplying to the values of f of x. In other words, for every single answer that we get for f of x, we're going to multiply by 2. Well, why is it the answer? Is because here 2 is on the outside of f of x. So it's outside of f of x, meaning that we calculate f of x first, and then we take it, we multiply by 2. So I'm going to sort of do the same thing, recognizing as sort of as above, and I want to plot my parent function too as well, or get some points on my parent function, because I know I'm going to need those values, because there's going to be 2 times it's just f of x. And then we're going to see what's going to happen there when we multiply the answers by 2. Because we're dealing with the square root function, I know that it's going to be that shooting arrow shape. It starts at a specific value. X is not going to have any negative values, or else we can't do a square root of a negative. So here we're going to say we start at 0. And again, one of those special points on our square root function that we easily calculate for what values of x. So that's going to be 0, 1, 4, 9, and 16. And that should be sufficient of points. Usually 3 or 4 is good, but we'll do 5 here. So let's calculate f of x first. So that's going to be square root of 0, which is just 1, Square root, oh, sorry, not 1, 0. I'm jumping ahead. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. And square root of 16 is 4. So again, I'm just going to plot the parent function so that we can compare s of x to my parent function. So there's my scale. So 0, 0, 1, 1, 4, 2, and 9, 3 will be right there. And again, the root function has this kind of shooting arrow and becomes a very flat shape to it. So there's my parent function. So let's label that f of x. So in order to go get my values for s of x, again, I could do the square root of all those things and multiply by 2. But this is why I came up with the values of f of x first, because I just want you to see that really we're going to take all my answers from f of x and simply multiply it by 2. Because here multiply by 2 is outside my function. Oops, 2. And outside my function means that we're taking the answer or the result of my function and then doing something with it. So in this case, multiply by 2. So 0 times 2 is 2. Not 2. Jumping ahead. 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. And 4 times 2 is 8. So here we're going to graph this now. So we still got 0, 0. 1, 2. So that's going to be up here. 4, 6 would be, sorry, not 4, 6. I'm looking at the wrong points. That's 1, 2, 4, 4. There we go. 4, 4. I'm looking at the, I mistook this column to be the x, but it's not. So there's my x's here. 9, 6. And I can't graph the rest, but that's going to be enough points to see that the shape is going to be like that. So here we can see that the shape hasn't moved up because here we have some common points, and really the vertical difference between the two graphs is going to vary. But really what the net effect is almost like we took this shape, it's anchored at the origin there, and we yank it up and it looks like there's a vertical stretch. Because really for every single y value that we get, we're simply doubling it. In this case, it's multiplied by 2, so therefore it looks higher, and it looks like it has the net effect of it being stretched. You know, a little bit of numeracy, right? Whenever we take a number and we multiply by a number that's greater than 1, in this case 2, we're always going to get a bigger number. So that's why this graph is going to be higher in some sense when what we multiply by is greater than 1, and so that's why it looks like a stretch. So the reason why I want to say that is because now on our next example, we're going to look at what happens when we actually multiply by something that's less than 1. Actually, I'm going to do two things. I'm going to look at also what happens when we multiply by a negative value. So here my parent function, so f of x is my cubic, x cubed. And c of x is going to be a transformation of f of x. That's what this means, but we know that in this case, it's a specific transformation to the cubic. So what happens when we take any number and we multiply it by a number that's less than 1? So a quarter, a half, even 7/8, 9/10, right? It's also numbers less than 1, and maybe it would be clear between 0 and 1. So absolute value is less than 1. Is that number is going to, the resulting answer is always going to be less than that number we multiply. It kind of makes sense because we're taking part of it. That's why we say fractions, or we're taking part of it. So here with a cubic, again, knowing our parent function, it has that sort of yin-yang shape. And again, we want to start at 0 because it's sort of that center, the middle of that cubic function. And then for there, we go up by 1 to get my key values of my parent function, and also down by 1 for the key values of that cubic. So here, I'm just going to label my axes on my graph first. So I get ready to graph this. 2, 4, 6, 2, 4, 6. And so what's 0 cubed? We got 0. 1 cubed is 1. 2 cubed is 8. And 3 cubed is 27. And then likewise with the negatives, negative 1 cubed is going to be negative 1. Negative 2 cubed is negative 8. And negative 3 cubed is minus 27. Okay, so let's just plot original function, see what it looks like. So here's 0, 0. We have 1, 1, 2, 8. So it shoots up pretty high right away. And we can't even plot 327 because my scale is by 1, so we can't get there. So let's do the negative. So negative 1, negative 1, negative 2, negative 8. So on the regular scale, we can see that the cubic is actually kind of really squished. And we're going to make sure when we get to the origin, it becomes flat and then goes up really fast again. So the cubic function looks something like that on a scale that is even. So how do we go off and graph c of x? So again, we could go off and recalculate all these things and then multiply by -4. But since I have the values for f of x already, we could just take that and really take each of these and multiply it by a quarter in this case. So again, we're multiplying by a quarter outside my function because the quarter, negative a quarter outside of f of x. So therefore we take the resulting answers of f of x and we multiply by negative a quarter. So negative 27 times negative a quarter is going to be 27 over 4, which is going to be 6 3/4. Here we get negative 8 times the negative quarter, which is going to be a positive 2. Negative 1 times the negative quarter is going to be a positive 1/4. 0 times anything is going to be 0. 1 times a negative 1/4 is going to be negative a quarter. 8 times a negative quarter is going to be negative 2. And 27 times the negative quarter is going to be negative 27 over 4, which is roughly around negative 6 3/4, so almost 7. So one thing I just want to stop here and highlight is notice that because we're multiplying by a negative value, all our original values that had a negative answer all of a sudden become positive. So negative 8 becomes a positive 2, negative 1 becomes a negative 4. So really you kind of see that these points, if they're on the bottom of the x-axis, they really jump to the top because they now become positive. So this is why we can see that this is going to be a natural reflection, because all the positive answers become negative and all the negative answers become positive. So sort of like I say, jumping the x-axis over to the other side. So let's go off and plot c of x. So we got 0, 0 still. Oops, let me go back. Get the red, 0, 0. And then we're going to have negative 1 and negative a quarter. So 1 and negative a quarter might be like right there. Let me blow that up so we could get a little bit more accurate. And then we're going to have 2 and negative 2. So 2 and negative 2 will be right there. And then we're going to have 3 and negative 6 3/4, so almost 7. So 3, 2, 4, 6 3/4 might be right there. And then likewise with the negatives, we get negative 1 1/4. So negative 1 1/4 might fall right there. Negative 2 and 2 would be right there. And then negative 3 and 6 3/4. So almost a 7 right there. So let's just connect that because we know it's a cubic, right? Therefore, it's going to have that general yin-yang shape. So that's going to how I'm going to connect the dots. And it comes really flat at the 0 and then goes up and down really quick. Okay, so with this one, it's actually kind of hard to see that this has actually been compressed. It almost looks like it's the same. But I just want to highlight that we know it's compressed because in the original function, we were only able to plot 2 points above the x-axis. But in our transform function, we're able to get that 1, 2, and 3. And really what you could think of it is that this point over here really moved down to there. This point over here actually is really because it's reflected, but I think of it as being compressed at the same time. It's really moved down to over there. So it's really coming down, it's being compressed. Although this point didn't actually map to that because it was a reflection. So really more accurately, this point over here actually reflected to this point over here. and then this point over here actually reflected this point over here. So really it became a lot closer to the x-axis. So this is why we can see it's actually being compressed or pushed down. And it's easy to see the reflection here. Here we kind of see that this part is reflected to this part over here, and then this part over here is reflected down to that part over there. So so that just kind of explains why when we multiply by a negative, in other words, outside our function, we have a vertical reflection. And when we'll multiply by the absolute value that is less than 1, in this case a quarter, we are going to get a compression. So that's a bit of the review, or that's the concepts in terms of vertical translations and stretches and compressions and reflections. And hopefully that's a little bit easier to see, especially when I do the f of x, is really because we're doing things outside our function. We're either multiplying or adding or subtracting something to it outside our function. So we get our answer and we're really affecting the answers. The next example is when we actually look at the horizontal things that are happening horizontally. It's a little bit more tricky. But hopefully our explanation will kind of clarify some things of really getting a true understanding of really what's happening to our function that results in something horizontal, in this case a horizontal translation. So let's go back to a parent function of f of x is the root x. And there we're going to look at h of x. So it looks different here now because it's f of x minus 3, but the minus 3 is inside the function. In other words, it's being applied to x first before we apply the function. And in this case, we're going to subtract 3 from x first before we take the absolute value of it, because again, that's what our function is. So how we could say that, another way we could say why it's inside the function is that right here, the negative 3 is inside the brackets. So inside the brackets is where it's defining what we need to do to x first before we apply our function to it. Okay, so this is inside a function. So what's the net effect? So I was a little bit efficient or lazy in creating this worksheet. Really, we're not going to look at f of x because it's not going to help us. Why is it going to help us? Not going to help us because we're not taking the answer of f of x and doing something to it. So we really need to do something to x first before apply it. So we're just going to do our straight points. So let me label the grid. So we got x and y. There's our scale, 2, 4, and 6. 2, 4, 6. So now we want to be strategic in choosing the values for x to graph this. And we're strategic in two ways. One is that we're recognizing that we're dealing with the absolute function. So knowing that the absolute function, what it looks like, it's a v, it's got the pointy end, and really the most important part, we can think of it, of that absolute function is where that corner or that pointy end of the v is. And we know that happens when we take the absolute value of 0. So notice I was careful here, and I didn't say when x is 0, but we want to take the absolute value of 0. So this is where we kind of look inside my function here and it says, well, how do I make what's inside my function 0? So there's that question that you guys ask over and over again. We know it's going to come up over and over again, is what makes something 0? Or in other words, what value of x makes it 0? So that's a really important question that we're going to ask again. So really what's inside my function is x minus 3. We want that to be 0 because we want to apply 0 to our function, in this case the absolute value. So in other words, we want the absolute value 0. So in this case we know that x must be 3 because 3 minus 3 is 0. So that's actually where our sort of middle point is, or we're going to say we want to focus on an absolute function. It's going to be 3. And when we look at the absolute function, when we find sort of that midpoint or that vertex, is we'll go up by 1 or go to the right by 1. So we got 3, 4, 5, 6. And then we go down by 1 on the other side. So it's going to be 2, 1, and 0. So here's the net effect of when we actually do this, is here, when we actually calculate this, and we'll start with 3, because that's where we start off with. This is obvious, because 3 minus 3 is 0. So we really take the absolute value of 0, which is 0. Here, when we do 4, when we do 4 minus 3, so again, we're subtracting 3 first, then we're taking the absolute value. So here we get the absolute value of 1, which is going to be 1. Here we're going to get 5 minus 3. And take the absolute value of that. So it's going to be absolute value of 2, which is 2. And finally, we're going to take the absolute value of 6 minus 3. which is the absolute value of 3, which is just 3. So we'll do the other side, or the other numbers here. We get 2. So 2 minus 3. So what's the absolute value of that? So it's going to be the absolute value of negative 1, which is 1. And then we get 1 minus 3, which is negative 2. So we know what the absolute value of negative 2, which is 2. And finally, we want the absolute value of 0 minus 3, which is going to be absolute value of negative 3, which is 3. So you might have recognized that, ooh, while we didn't start off with the same x values of our parent function, we didn't wind up with the same y values of our parent function. So that's one of the things that we sort of strategically chose the proper value of x. We sort of get the y values that we're accustomed to seeing on our parent function. So let's go off and graph this. So I'm going to start with 3, 0 first, because I said that, I recognized that was sort of the key part of my absolute function. So then I got 4, 1, 5, 2, 6, 3. And going the other way, I get 2 and 1, 1, 2, and 0, 3. And oops, I got 4 there. Missed it right there. And again, we know the absolute function is going to be a shape of a V. So we're going to connect the dots with a straight line. And so there, this is going to be h of x. So hopefully from seeing this, we could actually see why this is horizontally shifted to the right by 3. Because what we're looking at is that here, what's inside the function, we actually want to make that sort of map back to a parent function. In this case, how do we get 0 as a starting point from our absolute function? In this case, x has to be 3, so that's why it's kind of moved to the right 3. So that is horizontal translation. Hopefully, if you didn't understand that from grade 10, when we say, for example, we have y is equal to x minus 3 quantity squared, why is the vertex moved to the right 3? Hopefully you have a better understanding, because really it's the same question. How do I make this 0? Because the 0, when we're squaring 0, that's the only way we get 0, an answer 0, or an answer that's not positive in our vertex. So that's why that was a key point on there, and that's when x is 3. So that's why the vertex slides over, and it happens when x equals 3. So we're going to combine things, and notice that you might ask, well, why we haven't done a reciprocal function? Doesn't all this apply to the reciprocal function? Well, absolutely. So I'm going to actually take the hardest function to graph and actually apply 2 things to it. So here we have p of x is going to be f of x minus 2. So minus 2 is inside the function. We're going to subtract 2 from x inside the function. And then we're going to add 3. I realized I didn't go back and do the expression up here. So let me go back and do that, because this one is a bit tricky. So again, with h of x is we want to place f of x with my function. So I want to replace f of x here with my function. So my function here is the absolute function. But what's inside my function, notice what am I taking the absolute value of? In this case, it's not just x, but x minus 3. So you can think of it as whatever's inside my brackets, I'm going to put it inside to whatever that function is. In this case, the absolute. So let's look at p of x here. So one of the things we're going to recognize is that, based on the work above, is that this graph is going to be shifted to the right 2, because what is going to make this 0, x being 2, and it's going to move up by 3. Okay, so first of all, let's work on expression. So we're going to place f of x with my actual function. So in this case, is the 1 over x, but in this case, we got x minus 2, or we're subtracting 2 from x inside my function. So that means this minus 2 is going to be sitting in the denominator with my x, because this is a reciprocal function. And then finally, we're going to add 3 on the outside. So that's how we write p of x as an expression. So going off and graphing the reciprocal function is really tricky. So what we're going to do first is actually, and I would encourage this, that every time you draw the reciprocal function, is draw the asymptotes. Okay, so we're really, again, understanding our parent functions and recognizing that the reciprocal has those 2 asymptotes, a vertical asymptote and a horizontal asymptote. So I'm just doing the scale here. And recognizing the parent function, the asymptotes fell directly on their axes. So the vertical asymptote was really on the y-axis, the horizontal asymptote was on the x-axis. And that's actually really convenient because when we shift the graph, when we just simply move a graph or translate the graph, if we're moving the points, we're also moving the asymptotes. So hopefully that kind of makes sense to you. If we're just moving the graph, like everything moves, and that includes the asymptotes. So here we're going to say that because this graph is moved 2 to the right, that means the vertical asymptote is also going to be moving 2 to the right. So it's going to be, oops, I want to do a thicker line so that we could see. So there's the vertical asymptote, right? It's going to happen at x equals 2. Well, the horizontal asymptote in this case used to be at y equals 0 on the x-axis, but in this case it's going to be moving up 3. So the vertical asymptote would be somewhere along there. And again, the equation for here, let me do that in regular ink, is y is equal to 3. And I'm just going to rewrite this. This is x equals 2. So this is really going to help us draw and really come up with points to graph this. So again, we want to be strategic in choosing our x value. So again, this part, we're not going to use f of x, not going to be helpful to us. Is that when we look at the reciprocal function, we know that it looks something like this. So in the two different quadrants, or opposite quadrants, we want to call it that. And the key points, the main key point we want on each of the curves in the reciprocal is this 1, 1, and then over here this was a -1, -1. So those were the two key points in our reciprocal. So I wanted to sort of, if you want to say, map or find what value of x in this case in my numerator, not to equal 0 because we don't want 0. We can't have 0 denominator. But in this case we want 1 because we want 1 over 1. So here we can say, well, we want x minus 2 to, in this case, actually equal 1. Well, what value x is that going to be? We're going to add 2 to both sides, so that means x is equal to 3. So really our starting point for one of the curves is when x equals 3. When we go to the right, okay, we're just going up by 1. So there's going to be 4. But when we move towards the asymptote, we want to go by a fraction. So in this case, maybe we'll go back by a half. So this is going to be 2.5. So now let's go calculate the p of x first. And let's do 3 first because that was the easier one. So this is 1 over 3 minus 2 plus 3. Well, 1 over 1 is just 1 plus 3. That's going to be 4. When x is 4, so this is going to be 1 over 4 minus 2 plus 3. So 4 minus 2 is 2, so it's going to be 1/2 plus 3, so that's going to be 3.5. In the other one, when x is equal to -2, so this one is why it's going to be tricky because we have a fraction, but notice that strategically we chose a good fraction because 2.5 minus 2 is just going to be a half, so we get 1 over a half plus 3. And again, the reciprocal means that we're just going to take that half and flip it, so that's going to be 2 plus 3, which is 5. So we got our 3 points here on one of the curves. We got 3, 4. So it's going to be, let me do this in red so it stands out a little bit. 3, 4 will be right there. And that's looking actually pretty good. Looking pretty accurate because we're on that quadrant and it's pretty close to the crosshairs of the, or where the asymptotes sort of intersect. Next point is 4 and 3/2. So we get 4 and 3/2. So again, that point looks pretty good because we did get closer to the asymptote, but we're not on it and we didn't cross it. So that's a good indication that that point is good. And then the next one is got 2.5 and 5. So 2.5 and 5. Again, we're close to 2, but not there. And our point is higher. So again, this is a good indication that that point is valid. So we're going to connect those 3 points with a curved line. And again, drawing our ends of this line really close to our asymptotes, but not touching it. So likewise with the other side, we want to find the value of x. In this case, that wants to be -1. because we want -1 in my denominator. So in this case, x minus 2, we want that to be -1. So again, adding to both sides, 2 to both sides, we're going to get x is equal to 1. So we want x to be starting at 1. And now with this other part of the graph, we want to go to the left by big chunks. So in this case, we're going to subtract 1. So we want to look at 0. And then on the other side, we want to go up by a fraction. So when we go up to this side, we'll go up by a fraction. In this case, we're going to go up by, let's say, 1 1/2. So what is our resulting values of p of x? So in case p of 1 is going to be p of 1 minus 2, which is -1. So we really, that's what we're looking for, plus 3. So 1 might divide by -1 is going to be -1 plus 3 is 2. Let's look at the 0 first. So 0 minus 2 is going to be a -2. So that's going to be -1/2 plus 3, which is going to be 2.5. And then going the other way, we got 1.5 minus 2. So again, this is going to be tricky. That's going to be minus a -1/2. So we got 1 over -1/2 plus 3. So the reciprocal of a -1/2 is going to be -2 plus 3. So that's going to be 1. So let's go off and plot those. So we got 1, 2. 1, 2 is going to sit right there. Again, this looks somewhat accurate, or they have a good feel about this, because now it's sort of like on the opposite side of the quadrant. Then the next point on my plot is 0, 2.5. So 0, 2.5. So it'll be right there. So again, this looks pretty good, because as we're going to the left, it's going to get closer and closer to that horizontal asymptote, but it's not quite there. And the next point we're going to plot is 1.5 and comma 1. So we get 1.5 comma 1. It'll be right there. And again, it's getting closer to that 2, but it doesn't touch it, so it's good. Now we're just going to connect those points with the other curve. It's going to look like that, with my lines getting closer and closer to the asymptote but not touching it. So there is how we graph p of x. Okay, so hopefully I explained that in enough detail, because I want you to understand where we're getting the points from. Later on, we get to 3.5. We're going to take another strategy, perhaps it may be how we could graph this. But for now, this is one way that we could do, in this case, just strictly translations, how we come up with that graph. So how could we want to summarize this unit? This section. It's basically, the idea is that given any parent function, f of x, so f of x is this sort of like a variable for a function. It has to represent a specific function. So in this case, it could be x squared, root x, absolute value of x, or 1 over x. That we could write this general form and function notation. That transformation of that function g of x is that, again, here's this a value that we remember from quadratic, is that we can multiply something to this function outside of it. We could also add something to this function outside of it. So we're given this attribute, I call them attributes a and c. But inside our function, we could also add or subtract something to x as well. So this is what the d. So going back to what we did with quadratics, you might recognize that, well, in vertex form, and I believe at that time you might have been using h and k, right? Where h and k is going to be my vertex, because so it's x minus h. Where h and k is my vertex, because h minus h is going to be 0. So that's how we're the 0 squared. That's going to be the lowest part of my vertex. So really, we just change the letters of the variables around. So really, this is synonymous with x minus d quantity squared plus k. If we're focusing just not k, sorry, c, if we're just focusing on a quadratic. So that's the same idea here. So when we have a, we're going to have a vertical stretch or a compression by a factor of the absolute value of a. In other words, if a is -3, it's going to be a stretch by a factor of 3. And we know it's a stretch because in this case, absolute value of a is greater than 0. It's also going to be reflected in the x-axis if a is negative. So something to remember from a quadratic. If a is negative, it's reflected. So the same idea happens here, but for any type of function, not just quadratics. It's going to be shifted up by c units. if C is positive, or shifted down by C units if C is negative. And finally, it's going to be shifted to the right by D units if D is positive, or otherwise it's going to be shifted to the left if D is negative. So that's how we could describe the transformations. So let's look at a couple examples and how that happens. So each function g of x, we want to identify the parent function, describe the transformations in both the form and function form and in words. And here we're also going to be able to try to specify the domain of g of x. So the first thing I like to do when we're given our function is sort of break it down. There's my a value. In other words, maybe first thing is identify the parent function so we can see what the different attributes are. So here f of x is actually my quadratic because we have a square there, so f of x is x squared. So ignoring everything outside the square, that's what going to be my a value is. That's going to be 6, and my c value is going to be -4. So I'm going to write that down. A is 6, and my c value is -4. And I just like to write these attributes down off to the side so that once I know them, it's just sort of like the quadratic formula. Once I see that, I can not look at the equation anymore and just focus on the values of these attributes and then know how it affects our function, or in other words, nail down the actual transformations. And here my d value is actually 3. Think of it as what makes inside my bracket 0. Don't focus on the -3, but focus on what makes inside my bracket 0, what value of x makes inside my bracket 0. In this case, the x value is going to be 3, so we see the d value is 3. So from there, we can list off the transformations. So because a is 6, it's greater than 1, so we're going to have a vertical stretch by a factor of 6. A is positive, so there's no reflection, so we're not going to mention that. I'm going to mention my shifts in one sentence, so this is shifted down in this case, and C is negative by 4 units. And here D is positive, so to the right 3 units. Okay, so there it is in words. So let's rewrite this in function notation. So here we're going to say g of x. So it's going the opposite way now. We have the expression, we're writing function notation. So everything that's outside my function, I'm going to write outside the f of. And anything that's inside my function, in other words, this is my square function, so inside the brackets there, x minus 3. Okay, so that's how we do that in function notation. Last is we want the domain. So the domain, well, we need to recognize the type of equation this is, or type of function. It's a quadratic. So just because the quadratic is transformed doesn't change the domain, because the domain is all real numbers for all quadratics. The next example, we have g of x is -2 root x of plus 3 plus 5. So let's identify the parent function. So f of x is in this case the square root of x. This is a transformation of the square root function. Hopefully it's clear why, because we have a square root there. Again, now we're going to pick off my various attributes. So there's my a, my c, and my d. Again, what makes that 0? So a is -2, c is plus 5, and then here d is going to be a -3, because the -3 plus 3, that's going to give me the square root of 0. That's what I'm looking for. So let's describe these transformations. So look at a first. So because a is greater than 1, we're going to have a vertical stretch by a factor of 2. Because a is negative in this case, we also have a vertical reflection, or reflection in the x-axis, however you want to phrase that. And then we'll look at our shifts. So this one is shifted up, since c is positive, by 5 units. And since D is negative, and to the left 3 units. So there it is in the transformation. And let's write this in function notation. So here g of x is actually equal to, so what's my a value? Negative 2. Write my f with big brackets around it. And then what's my c value? So that's outside my function, plus 5. And finally, what's inside my function is really you take that and just rewrite that inside the brackets. And we get x plus 3. Okay, so there it is in function notation. And last is the domain. So this one is more tricky because we're dealing with the square root function. And we know the square root function, the domain is not ER. The domain, in fact, if we sort of quickly graph this, the square root function looks like the shooting arrow. In fact, it can only be x greater equal to 0. So it can only be 0 or positive. But in this case, because we know that we shifted this left 3, that's also going to shift this graph to the left by 3. So therefore, that affects my domain in that all my possible x values now shift to the left 3 as well. So in this case, x can be greater than or equal to negative 3. And we could kind of hopefully see that because if we move it to 3, we could have negative 3. We could plug that into our equation as well. Negative 3 plus 3, so that actually works. We get a 0, so negative 3 is allowed. And in this case, anything greater than negative 3 works. So there's the domain for that. So the homework for this section is quite a bit because I really want you to sort of practice this and get a really good understanding of doing these various translations and vertical reflections and stretches and compressions, and get a good feel of that, because really that's 3/4 of the transformations. And we're going to spend our next section actually talk about the last one, which is the new one and a little bit more difficult to comprehend.